The solution to this problem is going to have you saying, you got to be kidding me. This is 1227 airplane seat assignment probability. Um, Although this problem is classified as a medium and is found within the dynamic programming tagged list, it's not a medium, and I wouldn't really consider it a dynamic programming problem, at least the optimal solution. Um, this problem is hard. This problem is very difficult. It requires a strong, you know, mathematical kind of background, a strong understanding of, uh, kind of, induction kind of proofs, right? Maybe a discrete math background would be extremely helpful. This is just a very difficult problem, and you really have to structure it appropriately if you want to find the relationship that leads to the answer. Um, I spent quite a bit of time just trying to formulate the relationships between each of the components without being able to truly find the answer. So that's something you need to consider when you're solving this problem, that finding the relationship between elements and what that means will make more sense in a moment is crucial. Uh, but with all that said, let's go ahead and get right into the problem. So you're given n passengers that are boarding on an airplane with exactly n seats, right? So there's n passengers, there's n seats. You've been on an airplane before. You're familiar with this idea, right? You have a ticket, probably has a seat number, you go sit in your seat. The first passenger has lost their ticket and picks a seat randomly. But after that, the rest of the passengers will take their own seat if it's still available and pick other seats randomly when they find that their seat is occupied. Return the probability that the last person, the nth person, gets his own seat. Okay, so when you think about this problem, you realize pretty quickly or intuitively that there's this cascading effect, right? Because the first person at randomly is going to choose a seat. It's possible that that person chooses their own seat, right? And if that person chooses their own seat, then we're good, right? If the first person, person A, chooses their own seat at random, then everyone else who does have their ticket will choose their own seat as well. But if first person doesn't choose their own seat, well, then they're going to be in someone else's way, right? They're going to be taking some other individual's seat, and that some other individual is going to see their seat taken, so that some other individual is going to take some other person's seat, and there's going to be this cascading effect, right? So how are we going to capture that, within our formula? And when you try to write it out, usually, you have these kind of relationships, right? You say like, there's this probability that I'm going to be in this universe where I pick my seat. There's this probability that I'm going to pick this other person's seat. There's this probability that I'm going to pick this other person's seat. And then you can kind of branch out like that. And then if it's dynamic programming, you can figure out if there's intersection of branches and kind of work back. Or you can, brute force and calculate the probabilities that way, right? That's usually how we approach these kind of problems formally, right? And also intuitively, it just makes sense, right? Try to break it out into the universes of what's possible, right? If I take this seat, then what will that mean? If I take this other seat, what will that mean? Etc. Right? And that's what's kind of weird about this problem, right? Because when you try to think about it, the I'm gonna walk through what I kept running into and kind of show you why this is so difficult, right? Because you think about it in terms of trying to split it up, right? So if you have n people, right? Well, let's just say there's these seats, right? So there's these seats A, B, C, all the way to, I don't know, n, I guess, because there's n people. And then there's this first person, right? Now, this first person is what's throwing a wrench in the system because this first person doesn't have a seat. So they're going to pick one at random, okay? Well, it's possible in the best case scenario, right, this person that picks a seat at random actually ends up picking the seat that was allocated for them, right? So in the best possible situation, with a probability of what, this will occur. Meaning you have these n seats still, right? And this person ends up in their actual seat, right? And if this person ends up in their actual seat, well, then we're in good shape, right? Because this person won't get in anybody's way, so then subsequent people will also get in their seat, right? B will see their seat open, they'll get in their seat. C will see their seat open, all these people will, and then N will as well, right? So that's the ideal situation in terms of, it's the easiest case to understand, right? Because like if I get my own seat, then everyone will get their own seat. It simplifies the problem completely. So that's probably where you're going to think, what you're going to think about first. But also, what's the probability of this happening? Well, I have n seats I can choose from, and A is going to choose them all uniformly at random. So that means there's what probability that they choose this seat? Well, 1 out of n times they'll choose this seat, right? Just simple probability. Right, I have n options. I choose any of them at random. The probability that I choose one of them is 1 out of n, right? So this happens with 1 out of n times. Okay, but what about the other cases? Well, in the other cases, I don't choose my own seat and I'm creating an issue, right? I don't choose my own seat, n minus 1 over n times, right? Only 1 out of n times randomly will I choose my own seat. N minus 1 over n times, I'm going to end up choosing the wrong seat, right? Now, what does that mean, though, in terms of what the cascading effect is, right? Who's going to be affected? Well, that essentially means here I chose, I could have selected any of these seats at random, right? A could be anywhere here. Well, A could be, if A's here, what does that mean? Well, that means B will have to choose a seat at random, right? Because now B's screwed. B's in a bad position because I took B's seat. But so that's kind of a unique case in itself as well, right? So that could happen with 1 over n. And then, well, there's also the case where, I take C's seat, and if I take, C's seat over here, then B will be able to sit down, but then down the line, right, C's going to have to make a decision about what seat it takes. So that's what really adds a lot of complication to solving this problem, right? Because it's not just an easy relationship like this, right? There's cascading effects depending on what seat I take, right? If I take A, if A takes its seat at random, then it's easy, it's gravy. But if A takes another seat, well, it depends on what seat it takes that's going to affect the relationship, right? If it takes seat B, well, then seat B is going to have to do a random operation. If it takes seat C, well, then B won't have to do a random operation, but then C will. So then you just start getting these crazy spirals, and I don't know if I still have it drawn, but, this is kind of my work prior that was, leading to something that became too complicated, right? Because I was thinking like, well, if A goes with A, it's good, right, for a case of 4. But if A goes with B, well, then B is going to have to make a random choice. But if A goes with C, well, then B won't have to make a random choice, but then C will. If A goes instantly with D, well, that's a problem, and we'll talk about that more. But see, it starts getting spiraled out of control, and it's really hard to capture the relationship of how we're actually going to solve this, right? So let's go back to this example. So what I decided to do instead was, let's just draw out a case of 4 and let's try to walk through it and see if that can, lead to any intuition in terms of the nature of the solution to this problem, right? Let's just look at a case of 4 and let's just walk through and see, okay, does this work? Does this work? What does this mean? What does this mean? Let's exhaust all possible things that could occur and then see if that indicates something about the nature of the solution to this problem, right? So this is a very time-dependent kind of scenario here, right? Because if I only have 20 minutes to solve this problem, I'm probably not going to have enough time to write this out, right? But if I have sufficient time, if I think I have sufficient time to write out the whole problem and I have nothing else to go after, right? I think I tried to do it this way and it's not making sense. It leads to something like this where it's all sporadic and I can't figure out what the answer is, right? It might be beneficial to just draw out a long example and see what kind of information that reveals, right? So this is kind of like a last-ditch effort, right? This is a last resort approach because it's time extensive. But if you have the time, it's not a bad idea to try it this way. So I just pre-drew this out because I don't want to spend the whole video trying to draw this out. But let's just say for this example, right, we have 4 people. So we have n equals 4, right? So we have n equals 4 people in this example. Now, what's happening here, right, is we have the selection of A. right? So A is the first person, and A is going to choose at random, right? A is not going to intentionally choose its seat. It doesn't have its ticket. So the first person A, second person B, the third person C, the fourth person D, and so on, right? But in this example, there's just 4 people. A wants to go in A seat, B wants to go in B seat, C wants to go in C seat, D wants to go in D seat. So 4 things can happen, right? Either A picks its own seat, A picks B at random, A picks C at random, or A picks D at random. Now let's think about what the consequences are of each of these things. The first 2 easiest ones to understand are the red and the green. Lines, right? Because if A chooses A, then we're good thereafter, right? Because if A chooses A, then B isn't going to choose at random. B is going to see its seat open, it's going to pick it. C is going to see its seat open and pick it. D is going to pick its seat and see that it's open and pick it, right? So this happens with 1 over n, or let's color it blue, that's fine. So 1 over n, in this example, 4, right? So 1/4 of the time at random, right? Because any of these actions can happen at random, right? Uniformly. A can end up here, or here, or here, or here. If A ends up just coincidentally at random in its own spot, then we're good, right? Because then everyone else will choose their seat accordingly, right? Because only A is picking randomly. Everyone else is going to see their seat open and they're going to choose it. The other way where this is easy to understand is, well, this red example, right? In this red example, which also happens with 1/4 probability, right? All these things happen with 1/4 probability. A is going to pick D. If A picks D, well, we're trying to find the probability that the nth person gets its own seat. Well, A picked D, so the nth person in this example is D. D didn't get its own seat. Therefore, D isn't going to ever be able to get its own seat, regardless of the rest of the orientations, right? Just the fact that B might go in B and C might go in C, and D can't go in its own seat, so this problem's already done, right? So if anybody chooses the last seat and it's not the last person, well, then the problem's over, right? So we don't need to extend on this example because it's already soiled, right? It's already broken. Return the probability that the nth person gets his own seat. The nth person is never going to get his own seat in this situation. So that's a big fat 0 chance of it working out 1/4 of the time from the get-go, right? These yellow ones, though, we're not sure, right? Because there's further kind of scenarios we need to consider and think about what does that mean for the problem. Well, let's look at this chain here, right? This chain starting here and going up. See if I can get this whole thing on the recording. Okay. So in this example, let's say that, with 1/4 probability, A will end up in B's slot. So what does that mean for B? So B's going to walk up to its seat and see that A is there. So B's going to choose at randomly what to do. Okay? So B at randomly can choose 3 seats. He can choose A, can choose C, or you can choose D. So he randomly selects a seat. And, in this example, what you'll notice is this is something you want to look at and think about here, right? So this is what's occurring here is important. And if it's not clear to you now, it will be later. And it'll really simplify how we can build a relationship in this problem, right, between the components. But you'll notice here that if B chooses A, well, then it's like A and B, they just swapped with each other, right? So since they just swapped with each other, now C can choose C and D can choose D, right? Like A took my seat from me, so if I just take his seat from him, then everyone else will be able to figure it out, right? In this example, well, if B chooses C, there's more to configure, so we'll not worry about that next. But then if B chooses D, well, it's the same thing as here before, right? If B chooses D, right, that's this here, right? If B chooses D, then the problem's over because we want the probability that the nth person gets its own seat, right? So again, if somebody tries to choose a seat, the last seat, and it's not the last person, that's going to cause this whole thing to fail. So we don't need to keep extending the problem. We just stop here, right? Now, what's the probability of these things happening? Well, 1/3 for each, right? Because B is going to have 1/3, right? He has 3 options. B can go to A, B can go to C, or B can go to D. So 1/3, 1/3, 1/3. In this top, right, it resolves the problem because they kind of swap with one another, right? A took the seat from B, so then B takes the seat from A, then everyone else will be able to figure it out, including the last person. In this example, B took the seat from D. D's the last person, so you can just nullify it there. You don't need to continue down that route because it's not going to lead to the solution, right? Because D will never get its seat now because someone's already sitting in it. Okay? Now here, what's happening? Well, now C is having trouble, right? Because now C's going to walk up and C's going to look at its seat and say, B's in my seat. So he's going to randomly choose a seat. Now, if C chooses A, again, it works out, right? So again, this is another thing that's weird that in a moment should make sense. But what's going on here is that there's kind of a swap, right? But now it's kind of like a further swap, right? Like, okay, A took B seat, B took my seat, so I'll take A seat, and then everyone else will be able to figure it out, right? So now these remaining seats are open so D can take its own seat. Here, if C decides to take D's seat, although there's only one seat left, it doesn't really matter, right? Same thing. Only D can take the last seat. If someone else does, it nullifies, so this becomes 0. And that's this branch. Let's look at this other yellow branch. It's very similar, right? What if A takes C? Well, what's interesting here, right, is there's not multiple choices here because B's going to walk up to his seat, see it's open, and he's going to take it. Only when we get to C do we now have to reiterate and do something random, right? Because A took C's seat. So everyone in between A and C is going to sit in their own seat, right? Because A took C's seat, so then when B walks up, B's going to get in its own seat. It's going to see it's open. A only conflicted with C. So now when C walks up, now we have this splitting relationship we have to think about. And again, if C takes A seat, then they just swap with each other, and we're good to go. But if C takes D seat, again, we have an issue. And this will happen with 1/2 probability, 1/2 probability. Let's try to get all the probabilities here written out. 1/2, 1/2. Okay. And again, this is a case where we start because we're trying to think about what that means for the nature of this problem. So this is an n equals 4, exhaustive example. And hopefully from this, we can kind of think about a few things which will simplify how we determine this relationship between the elements. Okay? So the first thing you'll notice, right, is what? What's the first thing you should notice? Let's just sit here and think about this for a second, how we're going to articulate this point to make it obvious, right? So you pick your seat. If your seat's taken, you pick a seat at random, right? So you try to pick your seat. Seat taken, then pick at random. Okay? That's how this works, right? Except for the first node, right? The first node is going to pick at random. But the observation you can make here that simplifies this problem really is, well, all these up arrows, you'll notice they're all good. It all leads to a good solution. And why is that? Well, if A chooses itself at random, then everyone else can pick their seat. Also, if anyone else who's conflicted by A selects A, it's going to resolve the problem going down, right? So, the thing here, right, is when B is conflicted because A took B's seat, B selects something at random, right? And there's a seat that B selects which will resolve this problem. One of B's seats will resolve this problem. If B chooses A, it instantly resolves the problem, right? If B chooses something else, it could resolve the problem down the line. But when B is in the scenario, if it chooses A, it resolves the problem, right? Same thing in this example here. When C sees that its seat is taken, if C chooses A, it resolves the problem. Okay, so what I'm basically saying is, for every case, there exists a chair that resolves the problem. And what I mean by that is, even from the beginning, right? At the beginning, the problem is that A doesn't have a ticket. But if A chooses A, it resolves the problem. When we get to B and B doesn't have a ticket, it chooses randomly. But if it chooses A, it solves the problem. And when we get here, and we're at C, and C is conflicted by B, but B is conflicted by A, it's still conflicted by A. If he chooses A, it solves the problem. So for every case, when you choose randomly, if you choose the chair that's causing all the problems, it'll resolve all the problems. And that's one of the chairs. Right? So there's always one chair for all the chairs you can choose, which resolves the issue. And kind of generally, what this means is, well, let's look at this example here. Okay, when we have, let's say we have x to the n nodes. At the first time, x1 is going to select a chair randomly. So if x1 chooses xx, well, then everybody else up into xx will choose their own seat, right? x2 will see their seat and choose it. x3 will see their seat and choose it. x4, x5, yada, 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 all the way up into xx. If XX chooses its own seat, then the problem is resolved. If XX chooses X1, then everyone else will be able to find their chair and the problem is solved. But if X1 chooses some other seat down this line, right, because all these other seats have been chosen, then then those seats are going to have to deal with another conflict, right? So when we look at this first example here, what I'm trying to really get at, right, what I'm trying to articulate, which is so difficult, is that this person has 4 seats they choose at random, and one of them solves the problem. This person has 3 seats that they choose at random, and one of them solves the problem. And this person has 2 seats they can choose from, and one of them solves the problem. So every single person, they have n choices. One of those choices solves the problem. One of those choices nulls out the problem. And the other choices kind of push that problem down the line, right? This person has one choice that solves the problem, one choice that causes you to never be able to solve the problem because you sit in the nth person seat, and then it has choices in the center which extend the problem out. But that's true for every node, right? Every node is the same exact relationship. So even though this condition is different, where B in this condition initially will check and then choose randomly, at the end of the day, it's the same problem. B is going to choose 3 chairs at random. One of them solves the problem. Here, A is going to choose 4 chairs at random, and one of them is going to solve the problem. So if this is, let's say, let's create a recurrence relationship. We'll call it F of 4, right? F of 4 means that I'm going to have 4 chairs. I'm going to choose one of them at random and then see if I can get the nth person to get his own seat. Well, this problem, although it's different where B is going to walk up, it's the same thing. It's just F of 3. Right? This is F of 3 because it's, well, B's going to choose one of these 3 chairs and one of them will solve the problem. This one's a bit different because here B's going to choose its chair, but then C's going to have to choose one of the 2 remaining chairs, and that's going to be F of 2. Right? So really what this is, well, F of 4, if we're thinking of this in terms of F of X is choosing X chairs where one chair solves the issue, solves the problem. Right? If we think of that as F of X, well, F of 4 is, well, the probability of this happening, of it working out, is, well, I choose the right chair, right? So 1/4 of the time I choose the right chair. So I'm going to draw this more neatly, and I'm going to put it down here, I guess, so you can kind of see what's going on. Okay, so F of 4 is, well, 1/4 of the time it works out, right? 1/4 of the time it works out because I select this branch where I put A in the right spot at random. 1/4 of the time, it's never going to work out. So that's 0 times 1/4, right? 1/4 of the time, it's never going to work out because it's going to end up being 0. I'm going to end up accidentally choosing that last seat. Another 1/4 of the time, I'm going to lead to this scenario here, which is just f of 3, right? It's the same problem where I have one node B, where if it chooses A, if it chooses one of the seats, it works. If it chooses any of the others, it may not. But if it chooses one, it definitely works, right? The same thing for f of 4. If f of 4 chooses this top branch, it works. Otherwise, we're going to have to figure it out. This is the same thing here, right? This is the same. It's a sub problem. It's a sub problem based on the same thing. Even though the conditions are different, it's really the same scenario where you don't have your chair, so you pick one at random. You pick the one at random that works, it works out. If you don't, the problem gets extended or it fails. That's the same thing here. That's the point I'm really trying to articulate here. Is f of 4 and f of 3 are these scenarios are essentially the same because you're choosing a chair at random, and the one that you choose that fixes the problem. Ugh. Right. So this is just f of 3. And this is f of 2. Why? Because if you choose C, then B is going to choose its own seat, and then C will have to deal with this f of 2 case of trying to choose two things, plus 1/4 f of 2. Okay, so it seems like for any case, right? For any case f of n, if you choose the first seat, it works out. And that happens with 1/n chance, right? If you choose this seat, well, that happens with 1/n, but then the very next seat, you're going to have to consider, branching out. If you choose this seat, it's going to take n/2, right? Because what happened here, right? Why is n/1, n-2, et cetera, because if you choose B, then the very next person is going to have to randomly select a chair to try to fix this problem. If you choose C, well, the next person, B, will be able to select their chair, right? And then the next person, when C comes up, C is going to have to solve this F2 problem, right? So if I choose B, then B is going to have to figure out and play the same game. If I choose C, then B will have its chair available, then C will have to figure it out. If I choose D, then B and C will be able to figure it out because their chairs will be open, and then D, right? What I'm basically saying is if A chooses A, you're done. If A chooses B, well, now B is going to have the same problem of having to choose a seat randomly. If A selects seat C, well, then B will select seat B, and now C will have the problem. If A selects seat D, then if A selects seat D, then person B will select seat B because they'll see it open. Person C will select seat C because they'll see it open. And then person D will now be the one who has to deal with the problem, right? So this goes all the way down. And of course, there's the last one, 1/n, where it doesn't work out. So the recurrence relationship here, right, of this problem is, let's write it nice and clear for the people in the back. F of n equals, well, 1/n times it works out, plus 1/n times it doesn't work out, right? Because we're talking about probability here, right? 1 out of n times at random, it's going to work out. 1 out of n times at random, I'm going to select the last person on accident. It's not going to work out. And then I have this relationship here, where I'm going to try the n-1 person, the n-2, the n-3, all the way to the f of n-2, or f of 2. Right, and you can see that here, right? I always go down to f of 2. There's nothing lower than f of 2, right? Because f of 1, if I only have one choice, then I choose one person. So you can see here that it only goes to f of 2, right? It doesn't go below that because f of 1, there will only be one choice, so it doesn't make sense, right? I have to have at least two choices to choose from. If I have one choice or zero choices, then I choose nothing, right? I mean, there's no randomness, right? F of 1 is 1, okay? So when we look at this, I have 1/n times f of n-1 plus 1/n times f of n-2, right? I'm just reiterating this recurrence relationship here. But we could summation that as saying 1 over n times the summation of x equals 2 to n minus 2 of f of n minus x. Okay, so this is the recurrence relationship of this problem. This is the solution. Now, that's why this problem is so mathematically extensive and why it's so problematic to solve, because you're not going to do this typical relationship like I did before, where you're just like trying to draw lines and figure out how things are connected, because you have to really think about, well, although the condition is different for subsequent nodes, because they'll look first, and because subsequent nodes are going to try to, subsequent people are going to try to get in their own seat. But if their seat taken, it's really the same problem. Okay. So this is the relationship here. But then it's like, well, if f of n is based on previous things, how does this really help me, right? How is this going to make my solution more efficient? Well, then we need to think about, you know, using some tweaking and some special math here to make this problem more concise, and then try to see if we can find a solution that's not in terms of other versions of f, right? Because now it's f's in terms of f, right? So I guess this could be a recurrence relationship, but, you know, we're dealing with 10 to the 5 here in n. So, you know, this is going to grow pretty fast. So is there a way of tweaking this and finding an equation that's much simpler and faster to solve? Well, let's take a look. So usually when you solve these kind of problems, and I just know this from college, right, we're going to try to maybe iterate through another example of n and see if we can find a relationship between n and n plus 1, right? Since this is based off the previous things, can we find the next thing and then see what that means? So what would f of n plus 1 be? So f of n plus 1, so we just replace everything that's n with n plus 1. Now I'm going to just erase this because it's times 0. Right, it made sense writing it out because it really articulated, you know, what's happening in this problem. But let's not add any more terms than we need to, because you're about to see this is pretty complicated. So remember, we're replacing everything with n plus 1. X equals 2 to n. N plus 1 minus 2 would be n minus 1. And I'm not going to do all the algebra here, but, you know, just, you know, plug that in, right? I'm just adding a 1, so negative 2 plus 1, negative 1. And this would be f of n plus 1 minus x. Okay? Now, what I want to do, of course, right, to simplify this, is I want to get rid of this summation. So, you know, if we're going from x equals 2 to n minus 1 of this equation, can we make it look like this somehow? Let's try to see if we can do that. Okay, so this summation here is, well, for x equals 2, we have f of n plus 1 minus 2. For x equals 3, we have f of n plus 1 minus 3. And then we go all the way down to x equals n. So what I'm doing right here is I'm trying to draw out these examples to see if I can modify this so it looks more like this. That's essentially what I'm doing right now. At x equals n, I have, or x equals n minus 1, the last term, because I want the first term and the last term to agree. Why did I put 2 here? Because this has fn minus 1, so this should be 1, right? It should go to n minus 2 for the last example, but this should start at 1. So I apologize. Okay. So if we started at 1, that would be minus 1, minus 2, n minus 1 is the last term. And that would be f of n plus 1 minus n minus 1. All right, so if we simplify these, that means at x equals 2, we have f of n, x equals 1, damn it. X equals 2, we have f of n minus 1. And this is f of n minus n plus 1 minus n plus 1 would be 2, right? So n minus n, 0, 1 minus negative 1, 2. Okay. So how would we rewrite this then so it's not... Right, because we want it in the same form as the top one. Okay. So this summation is the same as... Right, this summation here is equivalent, right? If I thought about this summation in a different way, I could say, well, we start at... If we started at x equals 0... all the way to n minus 2 of f of x minus n. Or not n, x minus n, ugh. N minus x. Right? Because if you did this summation, like, so I found this relationship here by looking at this, right? So if I look at this one, I say, okay, when x is 0, we get n minus 0, that's f of n. X is 1, we get n minus 1. X is n minus 2, we get n minus 2, f of 2. So basically what I did is I formed, you know, using this summation, I found this thing on the right, right? And then I said, okay, well, that's equivalent to this on the right, on the left. And the reason why I'm doing that is I'm trying to make it look more like this one here, right? So that means I can replace right, I can let's just make this smaller. Right, so I can replace this summation with this summation here. So that's what I'm going to do. So I just copy this over. And what I'm saying is this summation is equivalent to this one here. Right? Right, these summations are equivalent when you just write them out. Right, and that kind of makes sense, right? Because all we're doing with n plus 1 is we're adding the f of n term. So this just adds the n term to this one. Right, but what I want to do is I want to replace this summation. So what I can do in order to do that, right, and I learned this in differential equations, which is why, you know, this problem is pretty difficult for someone who's not, you know, super mathematically aligned. But what I can say is, well, then that means f of n plus 1 equals 1 over n plus 1 plus 1 over n plus 1. I'm going to pull one term out so let's pull the 0th term out. So that would be x of 0 equals f of n minus 0, which is f of n. So that would be f of n plus, and then the summation just continues. But now it continues from this point forward. We can distribute this 1 over n plus 1. Well, actually, just to simplify things, I'm going to multiply everything by n plus 1 right now. So when you do that, I kind of want this to be standalone. It's so hard to know how much to write and how much to forget, you know? So we do that. This becomes 1. These terms go away. It just becomes a little nicer when we do it like this. Right? Except now we have an n plus 1 term over here. Right? So let's replace this term with this term. So in order to do that, we took this, we moved it over. What would we do to change this? Well, we multiply everything by n. All right, we multiply everything by n, like so. Then these terms, this becomes a 1. So this is n times f of n minus 1 equals this whole thing. right? So what I'm saying is you can replace this whole summation with n times f of n minus 1, apparently. Okay? So that means over here, since these are the same summations, right, I can replace this term with the same thing. So now you guys see why this problem is so difficult. Because it's so difficult just to find the relationship. And then when you find the relationship, there's so much math just to get it to a point where you have a solution that's not based on, earlier versions of itself or whatever. So that means we can replace this with n times f of n minus 1. Ooh, you scared me, Max. N times, sorry, that's my dog. F of n minus 1. Okay. Now these terms cancel. And then you're just left with n plus 1 times f of n plus 1 equals f of n plus n times f of n. All right. I'll write this part out because it's the kind of the best part of this problem. F of n plus 1 equals f of n times n plus 1. All right, so I'm just factoring out this f of n. And then if you notice, well, strangely, right, these two terms cancel. And you have the relationship where f of n plus 1 equals f of n. So this whole weird summation situation here, at the end of the day, is literally just itself. Right? And I'm going to leave it like this for now because it looks nice like this. So, well, what does that mean then? All right? Well, it can't be true in all cases, right? Because when n equals 1, there's only one choice. So if n is less than or equal to 1, we just return 1. But if otherwise, if n equals 2, it's a half. So what I'm essentially getting at here, which is so strange about this problem, right, is, well, f of 2 equals a half. And, well, f of 3 is going to equal f of 2. So that means it's going to equal a half. And then f of 4 is going to equal f of 3, which equals a half. So it equals a half. So everything's going to equal a half after 2. Right? Because the next one equals the previous one, with the exception of the first one. Right? But for 2, it's a half, because you can either choose the top or the bottom. So it makes sense that it's a half, right? Right, because you have two choices. Either you have 2 seats, you have half probability you choose the right one and the other one can get it. You have a half probability you don't choose the right one and nobody gets it. Like nobody gets the solution to this problem. Right, so for f of 2 equals a half, then f of 3 equals a half, f of 4 equals a half. So with the exception of 1, everything equals a half. So there you go. So what's the runtime in the space of this? Well, it's pretty obvious, right? For time, well, it's constant. You just make a comparison, and for space, well, it's constant. Right? And all that is based off of this insane relationship of looking at an example, right? So how do we solve this problem? We looked at an example. We kind of figured out what the recurrence relationship is by thinking about, well, it's really the same problem over and over again. We kind of looked at that, not too much. I figured we'd look at this more, but, the idea here is if you choose the right chair, then everyone else will choose the right chair. When you choose the wrong chair, everyone between you will choose the right chair until you get to you. If you choose the right one, then thing works out. If you don't choose the right one, then you just extend the problem. And that led us to this recurrence relationship. And then we used, some of our strong mathematical understanding, differential equation, discrete math, whatever you did to kind of learn these tricks, or maybe you're a prodigy and you know how to do these things, just naturally. We found that the relationship is, well, they're equivalent. And it starts at 1/2 and it ends at 1/2. So what I'm going to do, because I really like to create cool kind of picture representations of my problems. I'm going to move this all into one page. This is just me wasting time right now, so if you don't know what I'm doing or don't care, you can now look at that. Doesn't that look cool? Let's get this on description. All right, everybody, hope you have a wonderful rest of your day. Peace out.